using transient measurements. Now, in the face of growing competition, stringent emission regulations, and increased necessity for sustainable manufacturing, there is a clear need to focus on energy and resource efficiency. Now, in the processing and manufacturing industries, there's an increasing trend of industrial symbiosis where different organizations come together and share resources and materials in a mutually beneficial manner. However, as the process industry is embracing industrial symbiosis, this creates new challenges. For example, finding a feasible and optimal operation of such a system typically requires information about the entire process in the form of the process models, the economic objectives, real-time measurements, local constraints, and so on and so forth. However, the different companies might be reluctant in order to share this information across the different organizations, for example, due to intellectual property rights, trade secrets, and market competitiveness. Now, one potential solution that facilitates industrial symbiosis is the distributed optimization framework, where the different subsystems optimize their local objectives, and a master coordinator coordinates the different subsystems. Now, such kind of systems are commonly found in different applications. However, in this talk, we will focus on offshore oil and gas production optimization problems, where, for example, you could have different subsea wells that are producing from different reservoir sections that are owned and operated by different companies, but they share a common processing facility and they share common resources. Now, to briefly recall the idea of distributed optimization, let's consider an optimization problem where the cost is additively separable for the different subsystems. And we have a coupling constraint which says that the total resource consumed by the different subsystems must be equal to R. Now, we have two different frameworks for decomposing this problem. The first is the primal decomposition framework, where the idea is to split the problem into two subproblems and directly allocate the resource by using some auxiliary variable, say t, and the master coordinator simply updates what this value of t should be. And the economic interpretation of primal decomposition approach is that the different subproblems locally optimize their problem for given t and r minus t, and report the price they are willing to pay for the shared resource. And this is nothing but the Lagrange multipliers that corresponds to this constraint over here. So now, using this information, the master coordinator allocates the shared resource. However, when it comes to an industrial symbiotic network where we have privacy and data sharing issues, this may not be very favorable, since the direct allocation of the shared resource means that one has to, the different subproblems have to also report the local constraints such that the allocation does not lead to an infeasible operation. The second approach is the Lagrangian decomposition framework, also known as dual decomposition. Now, the idea here is to write out the Lagrangian by relaxing this coupling constraint using its corresponding Lagrange multiplier lambda. And then we would see that the optimization problem would be additively separable. So now we can split the into two subproblems and solve the two subproblems as a function of a given lambda. And the master coordinator updates the Lagrange multiplier lambda. Now, the economic interpretation of dual decomposition is that the master coordinator updates the price, which sets the price for the shared resource. And given this shadow price lambda, the different subproblems would locally optimize in order to maximize their local profits given the Lagrange multipliers. And the master coordinator updates the shadow price in order to reach equilibrium in this micro market setting. So we will be using Lagrangian decomposition framework, since this enables only limited information exchange, only in the form of the shadow price from the master coordinator to the subproblems, and only the total resource utilized by the different subproblems. So to repeat or to recall, the Lagrangian decomposition framework, we have a master coordinator that updates the shadow price based on the reported resource utilization by the different subproblems, and the shadow price is broadcast to the different subproblems. And using this shadow price, the different subproblems would just optimize locally in order to maximize their local objective and report back the shared resource utilization. And this is solved iteratively until it converges to the optimal solution. Now we have these different subproblems where we talk about solving a steady state optimization problem, but solving a steady state optimization problem also involves updating the models. Since we have uncertainty and disturbances, the models that are used in the steady state optimization have to be updated regularly. And one of the fundamental limiting factors of updating the steady state models is that we need to use data or real-time measurements corresponding to the steady state operation of the process. So typically there is a steady state detection, and only when the process is operating at steady state, then the process measurements are used to update the model, and then the model is updated, and then the updated model is used to solve the optimization problem. So one of the fundamental limiting factors of steady state real-time optimization is this steady state wait time. And this is because, for example, here is a data from one of the oil fields, and we see that the steady state detection algorithm that was used in this data discards large chunks of transient data points. So for example, here for one full day, the process has not been operating at steady state, and that means that the models are not updated for long periods of time, and that means the process is operating suboptimally for long periods of time. Additionally, the commercially used steady state detection algorithms also use some kind of heuristics such that the transient measurements could be falsely identified as operating at steady state, and by using these measurements, the model update would be erroneous. So how to address the steady state wait time? Well, one obvious solution is to use a dynamic RTO approach where we use dynamic models and solve a dynamic optimization problem. However, solving dynamic optimization problem is time consuming and computationally expensive, especially for distributed optimization framework where the different subproblems are solved iteratively. So in order to address the steady state wait time issue, we recently proposed what is known as the hybrid RTO approach, where the idea is to use the steady state models for optimization such that we only solve a steady state RTO problem, but we use dynamic models in order to update the models such that we don't have to wait for the process to reach steady state. Now, by using dynamic model for the model update step, we can use transient measurements such that we can update the models. And then once we have updated the model, we use the corresponding steady state model in the optimization in order to solve a steady state optimization problem. And we showed that for an oil and gas production optimization example, by using the proposed hybrid RTO framework, we can get a performance that is similar to the dynamic RTO approach, but at computation times similar to steady state RTO. So the idea here is now to extend the proposed hybrid RTO framework into a distributed hybrid RTO framework. So now, for example, each subsystem, we have a hybrid RTO framework where we have a local dynamic estimator that uses the dynamic models of the local subsystem in order to update the local models. And then we solve the local steady state optimization problem for a given shadow price lambda. And then we have local controllers that controls the local subsystems. And then we have this for different subsystems, and then the master coordinator updates the Lagrange multipliers based on the total resource utilization by the different subsystems. And here we also show this information boundary shown in these gray dashed box, which shows that the only information that leaves the information boundary and thus shared across the different organizations is the Lagrange multiplier, also known as the shadow price, and the total shared resource utilization. So we apply this to a oil and gas optimization problem where we consider 6 different wells, And we assume that there are 3 wells that are operated by company 1, produced from, say, one section of the reservoir, and we have 3 other wells that are operated by a different company, but they share the topside processing facility, and the gas lift, which is the gas that is injected into the well in order to boost production, is a shared resource that comes from the topside processing facility, and this is shared across the different companies. So here the optimization problem is to maximize the oil produced by the 2 different companies and minimize the cost associated with compressing the gas, subject to, of course, the limited resource constraint, the shared resource constraint. So now we can use the Lagrangian decomposition framework in order to decompose this problem into 2 different subproblems, one for company 1 and one for company 2. And we can use the dynamic models for the model update and use the corresponding steady state models, the local steady state models, to solve the local optimization problems. And here we have the simulation results where we compare the performance of the proposed distributed hybrid RTO framework and benchmark it with the performance by using a centralized hybrid RTO approach where the entire problem is solved as one big optimization problem. So on this side, first we show the total oil that is produced by using the different approaches, where the proposed approach is shown in black dashed lines and the centralized approach is shown in red solid lines. And we see that the performance is near identical. And when we look at the absolute error between the centralized approach and the proposed distributed hybrid RTO approach, we see that the absolute error is very low, meaning that you're able to get a very similar performance by using the distributed framework. And because we're using a distributed hybrid RTO framework, we don't have to wait for the steady state, for the process to reach steady state. And this means that we're able to optimize the process also during the transients by updating the models using transient measurements. In this plot, we show the total gas lift that is used by the different companies. And again, we compare it with the centralized approach, and we see that the performance is near identical, and which is also confirmed by looking at the absolute error between the centralized approach and the distributed approach, which is indeed small. And here we show the total gas lift that is allocated to the different companies, to the two companies. And an interesting thing to point out here is that the information that is shared across the different organizations is the total resource that is consumed by the 2 companies and not the individual allocation to the different wells. That is, so the information that is being shared across the different organizations is the sum of the gas lift resource that is used by company 1 and company 2, and the individual allocation to the different wells need not be shared across the different organizations. So to summarize, some of the main challenges of industrial symbiosis are sharing of information, where the different organizations might be reluctant to share information across the different organizations in the form of models, constraints, objective and real-time measurements, etc. And secondly, one of the challenges is that with industrial symbiosis is that the problem size could be much larger, and solving a large-scale optimization problem could be computationally intensive. And these 2 challenges could be potentially solved by using a distributed RTO framework, where we could split the optimization problem into smaller subproblems, such that only limited information needs to be exchanged across the different companies. And finally, when solving steady state RTO problems, we showed that one of the fundamental limitations is the steady state wait time associated with updating the models. And we proposed a distributed RTO framework using transient measurements, where the different subproblems use dynamic models for updating the models, and the corresponding steady state models are used in the local subproblem optimization. And by doing so, we showed that we can use transient measurements in a distributed optimization framework. Now that concludes my talk. Thank you.